Okay, we're ready to do some more identities today. Same process as yesterday, very similar anyway. As I mentioned yesterday, or on Friday, there's no set way to start each problem, so we have some pointers here to get us started. Number one, you can see, is pick the more complicated side to work on. Typically with identities with the equal to sign, we work on one side or the other. So pointer number two, if you can't make headway on one side, try the other side. Pointer number three, if you have one side has an indicated operation performance, if it says to multiply, go ahead and multiply them together. It says to add, go ahead and find common denominators, add those together, and so forth. Number four, if one side contains more than one function, try to write in terms of a single function. That goes along with kind of number five. What we've done so far is a lot of changes to sines and cosines. Oh, even further yet, if we can get down to one function such as all sines or all cosines, that might even make things more beneficial or easier to do as well. Jumping right into an example here, number one here, cosine of negative x times the tangent of negative x equals the sine of negative x, illustrates the opposite angle identities that we had on Friday that you added to your note packet. Cosine of negative x, just to make the point again, just equals the cosine of x. Tangent of negative x, we'll bring that negative sign out in front and just make that the tangent of x. From there, I hope we would all agree that we go ahead and leave the cosine as it is, but change tangent to put it in terms of sines and cosines. So we'll write that as negative sine over cosine, showing that cosine between the numerator and the denominator will cancel. That leaves us as negative sine of x over 1, or just negative sine of x, and as we have in our notes, negative sine of x equals the sine of negative x. Moving on, our next example says cosine squared times 1 plus tangent squared is going to equal 1. Probably just show one way, but anytime you have these squared terms, oftentimes they can be worked in more than one fashion. Here, cosine squared, very seldom, unless we change that to a sine squared, is that going to change. However, the 1 plus tangent squared we can change one of two ways. I'm going to go with the Pythagorean identity idea and change 1 plus tangent squared to secant squared. Again, that's a Pythagorean identity. Should allow us to make that substitution. And then if we look at our product identities, cosine times secant is 1. So cosine squared times secant squared is 1 squared, which is also 1. So we've reduced it down to 1. So as long as we knew our Pythagorean identity, that one was fairly simple. Let's say we started over and didn't know our Pythagorean identity. Somebody else might decide to change tangent squared to be sine squared over cosine squared. So another direction we could go with the same problem, just to illustrate a different pathway to get there. From here, again, we even have two choices within this problem. I'm going to go ahead and distribute, so cosine squared times 1 is cosine squared. If I take cosine squared times the sine squared over the cosine squareds, the cosine squareds will cancel, and I have sine squared. And then if we know that Pythagorean identity, cosine squared plus sine squared is 1. So as you can see, two different ways to work that same problem. Let's see if we can't work this the correct way. Go down to our third example. We have cosine squared over 1 minus sine of negative theta equals 1 minus sine theta. Starting out, go step by step. I'll leave the cosine squared as it is. I'm going to get rid of that negative angle. And again, I'll go piece by piece with this, but you can see that sine of negative theta is negative sine of theta, which I've written down here. Or a step further, cosine squared over 1 plus sine theta. Now, unfortunately, some of us might try to make the substitution, say 1 plus sine equals cosine. It does not. It has to be, those have to be squared, and it has to be a subtraction. So I'm going to change the cosine squared to its Pythagorean identity of 1 minus sine squared. That gets us to have our entire expression written in the same function, all in terms of sines. Now again, as an unfortunate math situation here for us, we can't cancel straight up and down. We can only cancel like factors, and we have a sum or difference here, so we can't cancel the individual terms. However, we can factor 1 minus sine squared as the difference of two squares, 1 minus sine times 1 plus sine, and that will be over 1 plus sine in our denominator. Just up to the top here, right up above, I'm going to illustrate that very quickly here. We all remember how x squared minus 4 factors to be x minus 2 and x plus 2. It's the same idea here. 1 and sine squared are both perfect squares, difference of two squares, so we factor the plus and minus. And then you can see, at least I hope you can see, that the 1 plus signs will cancel, and we're left with 1 minus sine, which is what we were trying to get to when we started the problem. So there again, using our identities along with our algebra skills to go ahead and simplify or prove one side equal to another one. Moving on, we have a couple more that we can do here as practice. Cosecant over sine plus secant over cosine. Let's start here with our cosecant. I'm going to change cosecant to be 1 over sine. That's still being divided by sine. Plus, change secant to be 1 over cosine. And leave my denominator as cosine here. I'm going to simplify each one of these individually. So I'm going to take this. I have one fraction divided by another, which means I have 1 over sine multiplied by the reciprocal of this. Well, the reciprocal of sine is 1 over sine. And I'm going to repeat the process with my second fractions, plus we have 1 over cosine being divided by this term. When I divide, I multiply by the reciprocal. Reciprocal of cosine is 1 over cosine. And you can see there, if we multiply those two, we'll wind up with 1 over sine squared plus 1 over cosine squared. So moving down here, what most people are going to say to do is go ahead and change that to our cosecant and our secant. Unfortunately, we still have this plus sign here, so changing those cosecants and secants just as yet probably doesn't make a lot of sense. But what we can do is take those two terms and find a common denominator. That common denominator is sine squared times cosine squared, which means my first numerator would become cosine squared. I have to multiply this fraction by cosine squared. My second numerator, plus, would become sine squared. Now, if we're paying attention or know our Pythagorean identities, cosine squared plus sine squared is 1. And now, in my denominator, I have a product instead of that sum that we just had 2 steps ago. So I'll break that into two separate fractions as 1 over sine squared times 1 over cosine squared. Just as a check, if I multiply this back together straight across, 1 times 1 is 1. Sine squared times cosine squared is sine squared cosine squared. But that gives us one more step to our final answer here, because right here, 1 over sine squared is cosecant squared, and 1 over cosine squared is secant squared. And this is the same product as we have up here, just in opposite orders. 3 times 4 is the same thing as 4 times 3. So we have our identity proved on that side. Sliding down, I think we have one more example to go here. This one, we have 1 minus 2 sine squared plus sine to the fourth equals cosine to the fourth. If you notice here, we have 1, 2, 3 terms separated by addition or subtraction. 3 terms separated by addition or subtraction is called a trinomial. A lot of our work in Algebra 2 with a trinomial was spent factoring that trinomial into 2 blank binomials. So that's what I've done here, set up 2 blank sets of parentheses. In the factoring process, what we're essentially doing is reversing the FOIL process. So reverse FOIL, the first terms I put in my parentheses here are what I multiply together to get 1. Well, that's pretty simple. 1 times 1 is 1. Okay, first terms. I jump to the second terms of my parentheses here. That's what I multiply together to get sine to the fourth. Well, to get sine to the fourth, I take sine squared times sine squared. Finally, to get sine to the fourth, a positive sine to the fourth, I can take a positive sine squared times a positive sine squared, or I can take a negative sine squared times a negative sine squared, because negative times negative is a positive up here. So knowing that we want to have negative 2 in the middle, we want our outer and inner products to be this negative 2 right here, which means both of those have to be negative. If both of those are negative, when I FOIL that out, 1 times 1 is my 1. I have negative 1 sine squared, negative 1 sine squared, or negative 2 sine squared, and a positive sine to the fourth. So we factored that. If we know our alternate forms of the Pythagorean identity, we have a cosine squared here. We have a cosine squared here. They are being multiplied together, so that equals cosine to the fourth theta. So again, noticing or pointing out the fact that if we are able to factor, it becomes a fairly simple problem, but it does require some factoring. Looking back at these examples that we've done, each one, as you can see, has started a different way. Here we factored. Here we made some fractions, found some common denominators. On the previous page, we used our opposite angle identities, changed the sines and cosines. Here we went ahead and multiplied with a little bit of a change. Here we did some Pythagorean identities as well, along with factoring. So you've seen several different ways to start the same different problem. So each problem starts differently, which is what you're going to need to be able to do.